It's my pleasure to introduce Professor Rafa Latawa from the University of Warsaw, who will be giving the Kolmogorov lecture. Rafa is an expert in high-dimensional probability and is an unasymptotic study of random processes. He has made substantial contributions to probability in general and to these fields in particular. To name a few, he proved with Bednar's the Bernoulli conjecture, characterizing the supremum of the Bernoulli process. This was one of Talleyrand's famous conjectures. He actually even received a money prize from Talleyrand for it. And Talleyrand said about the proof that it is simply stunningly beautiful, which really says a lot about Rafa. His work was published in Annals of Mathematics. So in addition, Rafa also contributed a lot to random matrices. He actually had the correct vision and intuition to make the correct conjectures about the behavior of the norm of Gaussian matrices, and he ended up proving these conjectures 15 years later, and this was published in Invenciones. So more importantly, actually, Rafa's contribution also really set the stage for many of the exciting recent developments in these fields. Rafa received many awards. I'm not going to name all of them. Just to name a few, he was a recipient of the Stefan Banach Prize in 2002. He was an invited speaker in the International Congress of Mathematics in Beijing in 2002. And most recently, he was awarded the prize of the foundation of the Polish Foundation for Science. Right? Please join me in welcoming Rafa Latawa.
Is it working? Okay, now. Okay, so thank you very much for the invitation, and it's a great. Okay, first the picture. Yeah. So I start with advertising the conference, next Stochastic Processes and Applications conference in Wrocław. The registration is open, or actually pre-registration, so you may go to the web page. And I was asked by the main organizer, Krzysztof Bogdan. Okay, so let's go back to my talk. So thank you for this opportunity to this distinguished lecture, and I'm a bit ashamed of seeing such audience in early morning. So I was hesitating what subject to choose, either give you some technical talk on research developments or give a review talk. So I prefer to give a review talk. So not all of the results are fresh, but I have some hope, but maybe some of them will be useful for you. Okay, so I will be talking about random chaoses or multilinear forms. And multilinear form is just combinations of products, and it's linear in every variable, and such form is also called homogeneous tetrahedral chaos. Homogeneous is obvious. Tetrahedral means that it doesn't contain squares. So this will be the main subject of my talk. I will review several estimates, both in the real case coefficients and more general normed space coefficient. But I will also go to quadratic forms when squares appears and general polynomials in Gaussian variables. Okay, let me start with a bit of notation. So the norm P, it will be always LP moments. So in the case when random variable is norm space value, this expected value of a norm to the P, to the 1 over P. By letter C, I will denote absolute constants. If there are some parameters, it means that they depend only on the parameters. Asymptotically bigger or equal, it means that there is comparison up to a constant, absolute constant. If approximation F tilde G means that F, both G approximately dominates F and vice versa. And if there are some subscripts, it means that constant depends on these parameters in the subscript. As usual, Gi will be normal random variables, and epsilon I will be Rademacher's, or probably at the Bernoulli Congress, I should call them symmetric Bernoulli random variables. Okay, so I will mainly be speaking about moments, but there is a strict relation between moments and tails. So one-sided implication is trivial. By Markov inequality, you always have a probability that random variable is bigger than e times LP moment is exponential in p, in minus p. But you may reverse this inequality using Paley-Zygmunt inequality, but you need to know that two-piece moment is compared to piece moment. In all of examples I will discuss, this will be the case, basically. So when the constant depends only on this parameter lambda, and if you have like a polynomial type equivalence of moments, this gives you some estimates on tails, and if there is p to the rk in moments, then there is a term t over ak to 1 over rk in the tail. Yes. Okay. So you will see example soon. Also, there is in this field there is so-called symmetry assumption quite often used. Namely, it does xi xj is equal clearly to xj xi. So you may either sum over all increasing sequences of indices I1 id, or sum over all sequences I1 id. But then you need to assume that the coefficients are symmetric with respect to permutation of indices, and they are 0 to avoid quadratic terms when sum of indices is equal. So this is called symmetry assumptions. Sorry. And I will mainly talking about homogeneous case, but if you have homogeneous case, you may easily go to the general tetrahedral case, so the case without squares, basically because LP moments is up to a constant which depends only on the d sum of LP moments of these homogeneous terms. So if you have like constant plus linear terms plus quadratic terms, then piece moment is this constant, modulo of a constant or norm of a constant plus norm of a linear term plus norm of quadratic term, etc. To linear. Okay, so this doesn't work obviously for general polynomials if there are quadratic if there are squares, but for tetrahedral case it works. Okay, so one of the main tools in this area is so-called decoupling inequality. There was a huge work done in the 80s, but a number of people. I will not mention all names, but first I think Fapien showed that LP moments of the sum, a decoupled sum, are the same, and then there is this beautiful result of Victor de la Peña, who is probably here, and Stephen Montgomery Smith, who showed that not only moments but tails are compared up to a constant, which depends on the order of chaos. Actually, it also works for you statistics, but I will not use this. And what is advantage here? So in the decoupled form, you have at each term in the product is independent of the other term. So you may use some kind of induction, yes? It's not obvious how to use this induction, but you may condition for example, on the second terms and third and d terms, and then you have linear form in the first term. Then apply some inequality for linear forms, and then go further. You decrease by one the degree. Okay, so sorry, I'm too fast. So probably here. So let me start with the simplest case. Sums of independent random variables is trivial, but I will start with trivial things. But you will see what to expect. So obviously for Gaussian, combination of Gaussian is Gaussian, and it's so LP moment is proportional to the LP moment of standard Gaussian random variables times L2 moment of coefficients. In the real case, so it is basically square root of p times variance. So this is equivalent to the fact that the tails is e to the negative t squared by variance. Okay, then Hitchenko and Montgomery-Smith somehow generalized this, okay, or used or find the similar estimate for weighted sums of Rademachers. So actually, Montgomery-Smith find the tail bound, and Hitchenko observes that it's equivalent to the moment bound. So there is a Gaussian term, square root of p times L2 norm, but this Gaussian term works only for small coefficients. So, and the first p coefficient, you should sum up the moduli, the biggest one. So this is the general situation for when you compare Rademacher to Gaussians. So the large coefficients, few large coefficients should be bounded by their absolute value, and the rest by Gaussian. Then there was Guskin and Kvapien generalization of this result extension to the case of variables with log concave tails, and they proven some formula, in particular for exponential random variable. This formula states that LP moments is like square root of p times L2 norm of coefficients, so Gaussian case, plus p times maximum of the coefficient. So this is like in Bernstein inequality. You have e to the minimum e to the t squared by the variance, minimum t times maximum of coefficients. Yes, so this is basically equivalent. Then there is a very nice result of Hitchenko, Montgomery-Smith, and Oleszkiewicz, who considered the log convex case, not log concave. So the typical example are viable random variables with heavy tails. So with the tails e to the negative tr when r is smaller than 1. And the formula is very nice because it's just a variance plus sum of LP moments of random variables to 1 over p. And there was a question if these formulas are just particular instances or there is some more general facts hidden behind them. And one of my first results was to find the formula. So if you sum either symmetric independent or non-negative random variables, then LP moment of the sum is equivalent to the Orlich time norm. So what is the advantage of this formula is that to estimate the moment, you need to estimate each of the marginals separately. Yes, so this is advantage of Orlich type formula. And if you don't want symmetric, you may, there are plenty of ways to symmetrize random variables. So for example, multiply by independent Rademachers, and then up to a constant. In this talk, I will not care about the constant. It's equivalent. So this formula also applies to the mean zero case. Okay, so now let's go to the chaoses, to the quadratic case. So if you want to understand something, you should first understand the Gaussian case, yes, by the central limit theorem. If you don't understand Gaussian, then there's no hope to understand something else. So for the Gaussian, it's like for exponential, yes? So if you have a centered quadratic form of order 2, then LP moment is of order square root of p times Hilbert-Schmidt norm of a matrix, so L2 norm of coefficients, to Schatten norm, plus p times the operator norm from L2 to L2, and this translates into tails that the tail of quadratic forming Gaussian, centered one is up to some point Gaussian, t square by Hilbert-Schmidt norm square, and after some point is exponential with constant operator norm. And this is there are several proofs. This is not very hard fact. So the easiest proof probably is to observe that Gaussian are rotationally invariant. So assuming that the matrix is symmetric, you may diagonalize it, and then when you diagonalize it, it's just sum of independent squares of independent Gaussian random variables, and then you estimate this, or you may estimate also Laplace transform, or use the concentration Gaussian concentration, there are several proofs. Okay, and this Gaussian inequality is strictly related to the famous Hanson-Wright inequality, which tells that the upper bound, the Gaussian the bond for quadratic forms in Gaussian random variables, is valid in the sub-Gaussian case. So when the random variables have sub-Gaussian tails, and it's obviously only the upper bound. And then the coefficient depends on this alpha sub-Gaussianity constant. And okay, it's named Hanson-Wright inequality, and I was for years sure that it was proven in Hanson-Wright paper, but I think Emanuel Mirman asked me a question. Okay, look at this paper, and it's not proven there. Okay, and because they proved this under assumptions that Aij are positive. Unfortunately. Also, their proof could be adapted to the case of not positive. So then Frank Barth and Emanuel Mirman showed how to do the proof in the general case, and then there is a very nice proof by Rudelson and Vershinin, which also do decoupling in a smart way, so they get a nice constant also. And okay, the idea of the proof of this, so I would like to show you how to get from Gaussian to the sub-Gaussian case. It's very simple. If you know decoupling. If you don't know decoupling, Hanson and Wright didn't know decoupling. So they need to use other tools. So first, you decouple the form. So okay, assume that there is nothing on the diagonal. The diagonal could be estimated in a simpler way because it's sum of independent random variables. So if there is nothing on diagonal, you may decouple. Then, trivial thing is that moments of sub-Gaussian are bounded by moments of Gaussians up to this alpha constant. So if you assume, for example, that xi and xj are symmetric and p is even, you take the p's power, then you have sum of polynomials, of even polynomials with positive constant, all are dominated by Gaussian. So you may replace this sub-Gaussian by Gaussian with the cost of alpha square, and then use the Gaussian result, and then go from moments to tails, as I was showing you on one of the previous slides. Okay, so now what about other linear forms? So forms in other linear random variables. So first is the Guskin-Kvapin result, or Hitchenko-Montgomery-Smith for Rademacher's true, or base counterpart, and it is. So if you assume that the variables are log conc, I don't know, there is a typo. There should be log concave. Yeah, they have log concave tails because minus log alt is convex on this slide. So then there is okay. If you look at the LP moment of quadratic form, then you take the variances of the rows, and you take like this Orlich norm or dual Orlich norm, like in Guskin-Kvapin, and then there is operator type norm, like in Hanson-Wright inequality, but this operator is not from L2 to L2, but from some Orlich space into Orlich space. And notice that this mi behaves like t squared. So for Gaussian, the tail is also t squared. So for Gaussian case, mi is t squared. So this is usual operator norm. Here is more complicated operator norm. So let's look how it looks in the Rademacher case. So in the Rademacher case, okay, you look at the variances of the rows. You sum the p's largest of them, then L2 norm times square root of p, the rest, so the Gaussian case, plus this operator norm. So, and the difference between Gaussian and Rademacher case is that you should additionally assume that coefficients are bounded by 1. Okay, so because the Rademachers are bounded by 1. Okay, so if you have log concave, then you may ask about log convex. And Montgomery-Smith, Oleszkiewicz, Hitchenko formula was simpler, so here also there is a simpler formula in the log convex case. And the formula is like this. So there's a Gaussian term, because log convex, they have harder tails than Gaussians. They have even harder tails than exponentials. Then there is like in the linear term, sum of LP norms of this Aij, Xi, Xj, and there is a middle term, p to the 1/2 sum of this. So you compute variances of the rows, you use them as a coefficients of Xi, and then use like one-dimensional results. So this is pretty nice formula, pretty easy, and let's look how it works in the in the Weibull random variable. So if you have a Weibull random variable with the tails e to the t to the r, and you are in the super exponential regime, then the LP moment is Gaussian moment times the maximum of all coefficients p to the 2 over r plus the maximum of variances times p to the 1r plus 1, 2, and there is a tail bound corresponding to this. So you may, so for example, if r is 1, there is p square root of p to the 3/2, and p to the square. And in the tail, there is t squared, t to the 2/3, and square root of t. And there is a corresponding Hanson-Wright inequality for sub-Weibull random variables, in particular for sub-exponential random variables. So it may be getting the same way how you infer from Gaussian case the sub-Gaussian case. Yes, you compare with the Weibull and decouple and compare with the Weibull, and it's up to alpha square like in the Weibull case, and also the tail bound is like in the Weibull case. So for example, in the sub-exponential random variables, there is a t squared term, there is a t term, there is t to the 2/3 term, and there is t to the 1/2 term at the end. Okay. So now let's go to the houses of higher order. And here the situation is much more complicated and starts to be notationally more involved. But let me first mention some earlier results by Christer Bohrer and Arcones and Ginet. So they showed that this homogeneous linear form in Gaussian random variables, here decoupled one, because it's somehow easier to work with the decoupled, is okay, there is square root of p terms, p term, p2 up to p to the d term, times some expected value of supremum of empirical process. Unfortunately, this supremum is over the tensor product of L2 balls, and it's not easy to compute it. Yes, and this was generalized to non-Gaussian case by Adamczak and Łuchowski. So the question is, can we get deterministic, instead of suprema of empirical process, some deterministic quantities? Okay, and you need some more notation. I will explain this notation in a moment in the case d equal to 3. But again, you have, if you have a splitting of indices, partition of indices into k sets, then you treat our multilinear form as a k-linear form on this on k sets, and the sets in J are treated as one index. So you treat this a priori d-linear form as k-linear form, and compute this tensor type operator norm. And then you take a combination with weights p to the k-half. So the theorem is that this is equivalent to the LP norm of Gaussian, and since this is a polynomial type, you get also the tail inequality. So for example, for houses of, okay, I will so this is general slide. I will go to the case d equal to 3 to explain how it works. Okay, so for d equal to 3, there are basically 3 times of partitions of the set 1 to 3. Either you may part into one set, and then you get L2 norm. Then you may part into 2 sets, and this is like operator norm, but you treat these 2 indices at 1 index. And there is a trilinear form, yes, and then this is. And MP of A is square root of P times L2 norm of coefficients plus P times these 3 terms corresponding to 2 partitions into 2 sets, and P to the 3/2 times this trilinear form. And if there are symmetry assumptions, these P's, these 3 terms multiplied by P are the same. Okay, and there is so under symmetry assumptions you have the house of order 3 is LP norm is square root of P times L2 norm of coefficients. So like Hanson right, then operator norm, but you treat 2 indices as 1 index, and then operator norm, but on a tensor product of 3. So tensor type operator norm. And the tail is t squared near 0, then t in the middle part, then t to the 2/3 at the end. And how the proof works, so maybe I should give some idea of the proof in the talk, this one. Okay, so the lower proof of the formula is induction. You decoupled, and then induction is straightforward to get lower bound. The problem starts with the upper bound, because if you try to do induction, whatever you use, either this Bohler type result or straightforward induction, you will end up into estimating like operator norm or tensor type operator norm of sum of weighted sums of Gaussians. So this is supremum of Gaussian process. So there is obviously this famous Fernig-Talagrand gamma 2 result, that this is equivalent to gamma 2 functional. But how to do different chaining? So this is the hardest part, to do the right chaining argument, provide and show that the upper bound is exactly what we need. Because, okay, the Fernig-Talagrand result doesn't tell us how to do the chaining. Okay, and I promise you to tell something about arbitrary Gaussian polynomials. So there is a beautiful result by Adamczak and Wolf, and they showed that for Gaussian case, you may reduce estimating arbitrary polynomial Gaussian random variables to estimating of sum of multilinear forms in random variables, where the coefficients of the sublinear forms are so the coefficients so there are some coefficients like a gradient, then Hessian, then third gradient, etc. So these are coefficients of this linear form, 2 linear and 3 linear form. So there is a way to get an estimate for arbitrary polynomial. Okay, so there are bounds for other classes of causes, and for formulas are more involved, so I will not torture you with them, but let me mention that this log-convex case works for arbitrary order causes, and then so for example, there is this for Weibull case, super exponential, there are formulas for arbitrary. Then if there is log-concave case, unfortunately, we are able to get only houses of order 3, and so in particular, Rademacher causes, which are pretty important in applications, are solved only for order 3, and there are some conjectures for higher order. But in the exponential case, we may get arbitrary order, because basically exponential random variables behaves like a product of 2 independent Gaussian. So this reduces to the Gaussian case. And also there are some results for non-negative case. Okay, and there are several open questions in the real case. Three of them concern 2 linear forms. So can you get estimates without assuming like regularity? can we get a tail estimate when moments are infinite? So there is a recent result by Buteros and Sambale, but they have some logarithmic terms inside, so they are not precise. Then probably most important is Rademacher dilinear forms, and also and more general dilinear forms in alpha regular random. Okay, so now let's go to the vector case, and again, let us start with linear combinations. So for Gaussian case, you may use the obvious thing, Gaussian concentration, and if you use Gaussian concentration integration by parts, it turns out that LP moment is like first moment plus square root of p times the weak variance. So what is weak variance is supremum over all variances after you putting linear functional of norm 2, of norm 1. And then so there is two-sided so inequality. So LP moment is like strong L1 moment plus weak LP moment. And there are formulas for Gaussian weak LP is square root of p times the variance. And then Dilworth and Montgomery-Smith noticed that this works also in the case of Rademachers. They applied Talagrand concentration on discrete cube. Then I applied other result of Talagrand, two-sided concentration, two-level concentration for exponential, and gave a similar thing for log concave tail situation. And then with Koch, we observe that we don't need to assume log concavity, only some regular sublinear growth of moments. But there's a pretty general result. So you only need to assume that the moments of xi grows regularly. It means that 2p moments is compared to p moments. So for example, all Weibull random variables behave like this with alpha equal to 2 to the 1 over r. Then the strong LP moment is like expected value plus the weak moment. And for weak moment, you may use the formulas I presented before. Yes. So this is this assumption of regularity is almost necessary for this formula, because in the sense that if this formula holds for IID copies of xi and with a constant doesn't depend on n, then there must be this regularity. And what is interesting in this result that it's not concentration type result. I mean that it is well known that if there is a dimension-free concentration, this was observed by Talagrand, then random variables must be sub-exponential at least. And this formula applies to the Weibull case, which is clearly not sub-exponential if parameter is below 1. So there is something more than just concentration of measure behind this theorem. Okay, and there is also equivalent statement in terms of tails. So if you have a look at the there should be no p at the tail of some vi xi is compared up to the tail of when you apply functionals up to after the teeth should be bigger than expected value. Okay, so there are several questions concerning linear case open. So first, in this result, there was always expected value of some vi xi. And if you would like to apply it in practice, probably you need to have some ways to estimate this. So for Gaussian case, there's this famous Fernig-Talagrand majorizing measure bond. And this bond was extended to some situations. So for example, Talagrand extended it to the Weibull sub-exponential. Then I observed that what is enough is log concave tails with delta 2 condition. Then with VTEC, the result was mentioned by Pierre. We established Rademacher case, so conjecture of Talagrand and Fernig. And then there is also a recent result by Bednosh and Martinek about infinitely divisible random variables. So in some particular instances, this is solved. But for example, in the Weibull case, when R is below 1, so super exponential Weibull case, there is even no conjecture what should be this expected value. I mean, I had some conjecture, but it's false. And there is another question: what if there is no alpha regularity? Okay, so let me now go into last 10 minutes into quadratic forms, vector-valued quadratic forms. So again, there was a result of Borres, Alcon, and Ginet. I cited it already, I think, twice. In the real case, so it was not necessary to assume in their work that the coefficients are real, but again, okay, so there is expected, so LP moment is compared to expected value, so this should be there. Then P times kind of operator norm, yes. But the middle term is expected value of supremum over something. So again, extremely hard to estimate, yes, because it's almost impossible to estimate. So can we get deterministic type here middle terms, okay, there is this trivial lower bound with deterministic terms. So you notice what is the difference, but the supremum is not under expected value, but outside expected value. So this is much easier to estimate. So there is like expected value plus square root of P times two terms plus P times something, and operator time knows, and the conjecture is that it might be reversed. So with Rabeck and Rafał Meller, we were able almost to reverse it up to this red term. So this red term is like sum of expected value, sum of Aij, Gij, which doesn't appear in the lower bound. So the question was, first question is this term necessary? And second, maybe for some Banach spaces, it's dominated by other terms. So let me explain the second question. Okay. Okay. So there is also Hanson-Wright type inequality. Okay. So there is Hanson-Wright will be on the last slide. So there is also a tail inequality corresponding to the bond, and the tail is almost two-sided. Unfortunately, there is this expected value of this Aij, Gij. So in the lower estimate, there is no this additional red term. And you may get rid of this additional term, but in the cost of logarithms, which is not that nice. Okay, and okay, we had a feeling that maybe for some Banach spaces, this sum Aij, Gij is compared to Aij, Gi, Gj. You may check it on hand that this is true in Hilbert spaces, because everything can be in Hilbert spaces computed by hand. So we asked this question to Marc Verrar, and he immediately replied us that yes, this property was considered before by Pizier, and Pizier called it Gaussian alpha plus property. So the Banach spaces that satisfy this inequality, that sum of linear forms in Gij are dominated in expectation by sum of two linear forms, are called alpha plus, having alpha plus properties, and there is almost a characterization of such spaces. So for example, if there is a Banach lattice, this is equivalent to finite cotype. So in particular, all RR spaces satisfy this with a constant of square root of R. Then in type 2 spaces, it holds. So there are a lot of examples of such spaces. Okay, so under these two alpha plus property, we have two-sided bond for quadratic forms. And also, okay, so in the LR spaces, you may exactly compute. So for example, in L2 space, which is Hilbert space, you may exactly compute these coefficients and have, without any expectations of Gaussians, here exactly what are these coefficients. Okay, you may immediately get from centered to non-centered Gaussian quadratic forms. It's because you added just linear terms, so it's not that big deal. But again, this additional term appears, which could be avoided in these alpha plus spaces. And there is a corresponding norm space valued Hanson-Wright inequality. So the inequality is like in Hanson-Wright, yes? You have sub-Gaussian random variables. You have minimum t squared by u square alpha force, t by alpha square v. V is like operator norm, so v is almost immediate counterpart to the usual Hanson-Wright. U is slightly more complicated, yes, because it's the second term is like Hilbert-Schmidt norm. In U, the first term is slightly more complicated, but there is this thing, and it could be reversed for Gaussians. So it's sharp up to a constant. And notice that so it looks slightly different than in the real case because there is this threshold on T. Yes, in the real case, you may easily check that U is this Hilbert-Schmidt norm, V is operator norm, but there is this threshold on T. But in fact, it disappeared because in the real case, this threshold could be dominated by Hilbert-Schmidt norm, and if T is smaller than Hilbert-Schmidt norm, then this term in Hanson-Wright inequality on the left, if C is sufficiently big, is bigger than 1. So probability is always smaller than 1. So below the threshold, inequality is trivial. So this is exactly Hanson-Wright inequality. In type 2 spaces, one may slightly simplify it because you may bound the terms using type 2 property and avoid Gaussianity. Also in LR spaces, these terms could be computed and okay. So let me finish with reviewing some other results without stating them precisely because I don't want to torture you with the formulas. So this two-sided board for quadratic terms extend to multilinear terms in Gaussian and also to polynomials using this Adamczak-Wolf trick. But unfortunately, you need to assume that the space is regular, so has this alpha plus property. So for example, in LR or in type 2, it works, yes? Or in lattices with finite cotype. Okay, then there are similar estimates for vector-valued linear form, multilinear forms in exponential random variables. And this is due to the fact I already told you that the exponential random variables are like a product of two independent Gaussians, so you may reduce forms in exponential to forms in Gaussians. And there is a recent result by Meller who obtained log concave case, but only in LR spaces, not in spaces with this alpha plus property, but in alpha. So, for example, in Hilbert spaces, he got it, which is still of interest. So let me finish with some open questions about vector case. So I think okay, so the first two are a bit technical, but I like them. So to get two-sided bonds, we needed to assume this alpha plus property. And I have a very strong feeling that it's not necessary, but we were not able to do it. What about non-Gaussian multilinear forms and polynomials? So there are two types of questions here even. So for example, is there like this log convex case, Weibull case, super exponential with vector valued coefficient, etc. And there is the third question is probably most important because norms of vector valued houses or or expected value of suprema of Gaussian causes appeared in many applications. So this is why they were considered by Kramer, Mendelssohn, Rauchus, for example. And there are only partial results. So Talagrand has a number of results. But they are not two-sided, and so upper bounds differ substantially from the lower bounds, at least in general settings. And Talagrand had some conjecture, but it's pretty complicated. But there is some conjecture, and it's pretty open, and I think it's important because it's like extension of this Fernig-Talagrand majorizing measure to the case of quadratic forms with Gaussian random variables, and it would be nice to have this result. And also, I believe that the methods in this result would also be related to the first question, that getting rid of alpha plus properties, because we. Okay, this everything is based on training, and I think the bounds for suprema of houses would also involve some training, and questions are pretty related. Okay, so thank you very much for your attention.
Thank you. Thank you, Rafa, for this nice talk. Are there any questions? Please.
Thank you very much for the talk. Concerning the first part of the talk about tetrahedral chaoses, can you explain, say a few more words about what you do if the chaos is not tetrahedral, that is, we have summation over the diagonals?
Okay, so it's unfortunately, okay, so the quadratic case is easy because the quadratic form, you have this two linear form plus sum of squares, and then this should be, sum of squares is sum of independent random variables, so this is easy. But if you have more general case, this is only done in Gaussian case, and there is this observation by Radek. And what is behind this observation? For example, take G square. So G is a sum of independent Gi by square root of n. Take the square, and you get sum of Gi Gj by n plus sum of Gi square by n. So the second term is almost a constant. And the first term is like, decoupled. So this was basically their idea, but they use smart tools, using Hermite polynomials and kind of Mariavin calculus where is hidden behind, but they were not using Mariavin calculus, but they, some expansion into chaoses. Yeah. And it's wide open in the non-Gaussian case, because you don't have this phenomenon, yes. But random variable square or third is a sum of linear combinations. Yeah.
Other questions? So I have couples. So can you say anything in the dependent case? Like
So unfortunately, no, it's everything depends, even in, So probably, I'm not a specialist, but suppose that you are looking at the decouple. So I guess there are some decoupling results. So in the decouple result, you may use some induction, yes? So if you have some result about, moments of sum of independent random variables, and you get the quadratic form, you may try to decouple, and then, okay, use the induction. But then you need to condition, yes? And then, there is this conditioning is also a problem. But maybe if you have some mixing some mixing conditions means that you are not losing too much after conditioning. Yes, there are some definition of mixing constants. So maybe this could be used, but I'm not a specialist. But I would think that probably such approach could be applied in some very regular situation for in that weak dependence.
Okay, and the Hansen right has been applied, for instance, to kind of the covariance estimation problem. Are there applications for the tensor case?
I think this paper of Mendelssohn, Rahut, and Kramer, their motivation was like this. Yes. So this is why they considered this suprema of chaos.
And maybe one last question, which is very vague, but can we interpret the right-hand side as being maybe some carré du champ of some nice, I don't know, well-cooked generator, Markov generator?
I don't know. Okay, I was thinking about these terms as kind of tensor of operator norms of tensor product spaces. Yes. So this is like dual norms to tensor products. Yes. So some, but maybe if you go deeper, you will observe something like this.
Okay. So if there are no more questions, let's thank Rafael again.
Lecture here, and in order as memory of Ruhr University knowledge from Bochum.
Thank you very much. Thank you.
So good morning, everybody. My name is Holger Dette. I'm from Bochum. It's a great pleasure for me to introduce to you Shoming Zhang. Shoming is a professor in the Department of Statistics at the University of Wisconsin-Madison. She earned her PhD in statistics from the University of North Carolina at Chapel Hill in 2000. And then she pretty quickly moved to Wisconsin, and she stayed there all the time. She had some research stays at other places, but she was spending her career there. And she's very well known for her work on statistical methods in computational neuroscience, biostatistics, and financial econometrics. She has also made very important contributions to multiple hypothesis testing, large-scale simultaneous inference, dimension reduction, high-dimensional inference, functional and longitudinal data analysis, and robust statistics. And I probably forgot some, so I apologize if I forgot something. Shoming is an elected fellow of the Institute of Mathematical Statistics and the American Statistical Association. And this year, she also became an elected member of the International Statistical Institute. She has served and is still serving on the editorial board of many of our journals, including the Annals of Statistics and the Journal of the American Statistical Association. Each year, IMS nominates 8 Medaillon lectures in fields across its subject range. The Wardour Medaillon lecture signals the honor inherent in being selected to give one of these lectures. IMS awards the Medaillon lecture to Shoming Zhang, and today she will present her lecture entitled, you see it, Learning Network Structured Dependence from Multidimensional Temporal Point Process. Thank you, Shoming, for your great contribution to our field, and thanks for coming to Bochum.
Thank Holder for the very kind introduction. I'm Shoming Zhang from Wisconsin-Madison Department of Statistics. I would like to express my gratitude to Professor Harold Dahling and the local organizing committee and the scientific committee for the hard work in arranging this IMS, Bernoulli-ims World Congress. I also want to extend my thanks to the IMS Committee on Special Lecture. Yeah, this is actually my first time to Germany, and it's a huge honor for me to speak at the Medallion lecture. I'm a statistician, and as a statistician, I find it both fascinating. Thank you so much. Yeah, I find it both fascinating and also extremely challenging to develop statistical learning methods, inference procedure, and also computational methods for analysis of large-scale, complex medical imaging data, including various types of imaging data in the computational neuroscience research, including the following. I have been working with this type of neuroimaging data in the past 20 years, like spatial temporal functional magnetic resonance imaging data, diffusion tensor imaging data, multi-channel EEG recordings, more recently some imaging genetics data in the Alzheimer's disease study, and also multiple neuron spectrum data. For the last one, multiple neuron spectrum data, yeah, actually, they are the primary mode of information transmission in the nervous systems. On the other hand, there were very, very little work by statisticians to address important scientific questions in this area. So in this talk, the focus is on exploring point process and probabilistic graphical models to understand interactions between neurons in the brain. So to begin with, I will first briefly review some related works on point process. So I have been working in this topic for about 10 years. So in the 2016 papers, we are using some discrete time modeling to develop statistical learning methods to analyze the functional connection among neurons using discrete time modeling. And in that approach, we choose the Poisson process to model the event counts in discrete time, in discretized time bins. While the discrete time modeling offers computational simplicity, they also result in some loss of information. So moving forward to the continuous time modeling, in this 2023, we utilize the inhomogeneous Poisson process to analyze asynchronous longitudinal data, where, what does that mean by asynchronous? That means the observation times of the response variable and the covariates, they are recorded at different time within each subject. So that's definitely one of the challenges. And in this 2024 work, it was inspired by learning the network structure dependencies underlying a class of non-stationary multivariate point process from the neuron spectrum data. And most of the recent work focuses on discussing the causal relations in multivariate point process data. Delays. Thank you. So this is a brief outline of this presentation. The first part, introduction, will review some motivation and background of the multivariate point process in our study. And the second part, we will develop some network structured model for the conditional intensity function, CIF. And in the third part, we will discuss some probabilistic property and stochastic mechanism of the proposed CIF model. And in the next section, we will discuss some statistical property of the procedure for training the CIF model, and also learning the network structured dependence. And we provide some numerical evaluations using simulation study and real neuron spectrum data analysis. And the last part is some brief concluding remarks and further discussion. All right. So what is multivariate point process? I happen to work with this topic in the recent 5 years. So multivariate point process refers to the random occurrences of a specific type of event. For example, the neuron spec-bearing contagious disease incidents, e-commerce transactions, and user postings on the social media over times. Usually they are represented as V vectors recorded at V nodes. So that big V corresponds to the dimensionality multivariate. And at each individual node I, the vector Ti signifies sequences of time points TIL. So every individual TIL represents the occurrence time of the else event during an experiment of duration big T. And what is the goal? In our approach, the key objective is to extract dependency structure among nodes within the network from the observed V sequences of event occurrence times. So as an illustration, let us consider the multiple neuron spectrum data. I haven't talked about some detail. I want to use a graphical illustration for a better illustration. So this figure 1 on the left-hand side, the plot has 5 rows. Each row corresponds to 1 neuron, and each neuron's spikes and silences are recorded, are represented along the time axis. So the spikes, the pattern of spikes are represented by the vertical line along the time axis. So as we can see, the spiking, each neuron's spikes are paired at highly irregular time points. So this is significantly different traditional time series. Time series, they corresponds to equally spaced time points. But here, when we talk about the point process, they are highly irregular spaced. And on the right-hand side, this is the network graph with 5 nodes. So each node corresponds to one point process on the left. And we see we use different color. So the color corresponds to different type of effects. So arrows indicate the interaction, different type of interaction. We use red color for the excitatory effects and the blue color for inhibitory effects. And what is the research goal? I put this question mark. We want to learn the network structure from the observed multivariate point process data. So this is a major question throughout the rest of the talk. And I also want to mention there is a research book titled Analysis of Neural Data, written by Robert Cass, Eden, and Emery Brown, published in 2014. It provides more background information, and I highly recommend this book. I myself benefit a lot from reading this book written by a statistician. All right, so let's talk about some more technical part. So to define the multivariate point process, let's start with the univariate case first. So univariate case corresponds to an individual node I. At each single node I, the point process is a list of strictly positive and the increasing time points up to the big time t. So this is the point process. And the counting process, NIT, is defined as the total number of event occurrences up to time t, including t. In order to capture this evolution of the point process, we can define the stochastic conditional intensity function, CIF, of the of the counting process, similar to the notion introduced in Rubin 1975 paper in IEEE transaction information theory. So this conditional intensity function is lambda I t given ft. Ft corresponds to the sigma field generated by all event counts up to time t and across all nodes. So I put equation 4 and equation 5 together because in this setup, they give the same definition for the conditional intensity function. So what is the interpretation? So intuitively speaking, the conditional intensity function represents the instantaneous rate of events per unit of time. So this is the formal definition of CIF. Then we can define the multivariate counting process, NT, which is a vector of V individual point counting process at V nodes. And similarly, we can define the total conditional intensity function of the multivariate counting process in this equation 8. It is actually the extension of the univariate case. So for the framework of multivariate point process, we are going to use the notion of orthogonality of martingale. Basically, it means the increments of the counting process at any distinct nodes are asymptotically independent. So in this lemma 1, we can learn that as long as the multivariate counting process satisfies the orthogonality of martingale condition, then the multivariate, the total conditional intensity function of the multivariate counting process equals the summation of all the individual conditional intensity function over all nodes. All right. So the outline of our proposed continuous time modeling includes the following 3 parts. So the first part, we want to develop some statistical modeling of the conditional intensity function. In the second part, we are interested in learning some stochastic property of the proposed conditional intensity function model and the multivariate counting process. And the third part is we are interested in studying some statistical property of the learning procedure for network structure dependence. In our procedure, we propose the continuous time model for the conditional intensity function using this functional form in equation 11. So this is purely a statistical approach for modeling this conditional intensity function. And in model 11, there are 3 parts, including the parameter beta 0i, beta gi, and some internal history-dependent covariate. They have the following interpretation. The baseline intensity parameter, beta 0i, is connected with each individual node i. Then the connection strength parameter, beta ji, quantifies the magnitude and direction of influence from parent node j on node I. Yeah, specifically, beta gi greater than 0, less than 0, equal to 0 corresponds to excitatory effect, inhibitory effect, and no effect, respectively, from node j to node I. For interpretability purposes, we also assume beta ii equal to 0 for all nodes I, meaning there is no self effect. Yeah, of course, this type of assumption can be relaxed. Then the network graph can be obtained by the edge set E collecting all pairs of nodes with non-zero connection strength parameter, beta gi. So this edge set can be separated in 2 parts. The edge set E plus for excitatory effect, and the edge set E minors for the inhibitory effects, because they corresponds to different type of influence. The harder part is how to induce some type of variable, because in this case, we don't consider external covert. Instead, we introduce some internal history-dependent variable. So we formulate this covariate XJT as some transformation of some empirical rate RJ site. Yeah, RJ site is given in equation 16 using some nonlinear shape function G and the time lag constant psi. So I would say this part is purely from a statistical modeling point of view. Yeah, recall the previous conditional intensity model links both the historical data and also the network structure. And by specifying different type of link, the shape function G, our proposed model connects with other existing CIF model. Yeah, for example, if we take the nonlinear shape function Gx to be the linear function x, then the model 11 can be rewritten as model 17. If we take a closer look at, we can see this is actually a special case of the multivariate nonlinear Hawkins process. If we set the nonlinear link function to be the exponential link function and using a specific type of triggering kernel. So this connects with the Hawkins process. In addition, we can look at another case. If we choose the G function to be the logarithmic growth function, log 1 plus x, then the model 11 becomes this model 19. And this model 19 agrees with a model in a 2015 AI stat paper. All right, probabilistic property of the proposed CIF model. Although I'm not a probabilist, I realize that how important it is deriving probabilistic property, stochastic mechanism of the stochastic conditional intensity model. Yeah, we have derived the corresponding theoretical results. They are very, very essential for us to study the statistical property of the procedure for learning network structure. So the details are provided in this paper. It is public available. So in the interest of time, I will skip this part. But I want to mention points of interest in statistical learning. I put 2 points. The first point is, if we really want to know what type of stationarity, then the thing is, the multivariate counting process in our setup is not a strict sense stationary. However, we can study some additional results. So theorem 1 tells us that the average rate nt over t for time up to t converges in probability to a deterministic constant, a vector C0. Yeah. In the literature, yeah, this type of stationarity is called asymptotic mean stationarity of the multivariate counting process. And also, there is an advantage, even if we don't know the explicit form of the limit vector, C0, this result will be sufficient for us to study statistical property of the resulting network structure learning procedure. All right, so our goal our goal, eventual goal, is to estimate the true parameter in the conditional intensity function and also reconstruct the true structure of the network. So in the true network structure, it includes, at each node I, it includes a vector. It's v-dimensional vector. And because we have altogether v nodes, so the total number of parameter is v squared. If v equals 100, then this is a large number of parameter. So we want to estimate the parameter from the observed multivariate point process data. And we want to use this loss function in this equation 23. This loss function at individual node I was derived from some negative log likelihood function together with the conditional intensity model. So as long as we can estimate all the parameter vector, we can aggregate the estimator and reconstruct the true network structure. Yeah, in particular, if we want to estimate an individual parameter at node I, we can use this penalized M-estimator, which minimizes the sum of the loss function and the penalty term. Here, we use the weighted L1 penalty. And then we can reconstruct a network by by collecting all the coefficients, all the estimated coefficients, which are non-zero. So this gives us the reconstructed network H hat E. It includes the hat E plus for the excitatory effects and the hat E minus for the inhibitory effects. Yeah, in addition, we want to study some asymptotic property for the statistical estimator in the structure learning. So we put a different type of conditions here. So the first result is talking about some consistency. So theorem 2 guarantee the existence of a consistent penalized M-estimator, and it converges to the true parameter vector at the rate square root 1 over t as t approach infinity. Yeah, next result, we are interested in the persistency property of the penalized estimator with zero parameter. So this equation 13 tells us that part of results. So if we want to estimate the parameter which are exactly equal to zero, then with probability tending to 1, that the estimator is equal to 0. Using the existence result and the persistency property, then we can obtain this corollary 1 concerning the consistency of the network recovery. So the corollary well confirms that the network structure estimator are consistent with the true edge sets. So this provides the support for the validity of our network structure learning procedure. Yeah, in the rest of time, I want to present some numerical experiments, including a simulation study and also analysis of real brain, real neuron spectrum data. In a simulation study, we consider 3 types of true network structure in this figure 1. So on the left, network 1 is a relatively simple network. It resembles the directed acyclic graph, DAG, to capture the information flow from the sensory neuron to the motor neuron. In the middle, the network 2 is a medium network with 20 nodes. So it mimics the potential hub-and-leaf structure commonly observed in the neuron ensembles. On the right, the network 3 is a complex network consisting of 50 nodes. So it is also DAG, sharing the same DAG design motivation as in network 1. So computation, from computational point of view, handling the network 3 will be more challenging because the number of nodes is 50. And in order to sample the event from the multivariate point process, we use the proposed conditional intensity model. So the detail is specified in 32. All right. We want to make a comparison with some other approaches. So we want to compare with discrete time modeling and some Bayesian methods. For the discrete time methods, it depends on the choice of the bin size. So in this table 1, we can see we can consider the bin size relatively small, 0.1, and relatively large, 0.5. And in the Bayesian approach published in the AI stat paper, it requires specifying the maximum number of parents. So the number of parents could be 2, could be 3. So this table 1 summarizes all the methods. In our method, we use continuous time modeling using penalty, either weighted L1 penalty or just L1 penalty. And all methods using the time-lag constant and the nonlinear shift function for parameter estimation adopt some empirical choices. In the simulation result, we consider different time lengths t, ranging from relative small 500 to 1,000 and 2,000 time units. And we compare, we use the performance criteria of each method using correctly detecting number of excitatory and inhibitor result. So this includes correctly detected number excitatory effects and correctly detected number inhibitor results. So the first 3 criterion reflect the level of sensitivity, and the bottom one, connect node, corresponds to the level of specificity. So in this table 1, we use the network, complex network with different connection strengths, beta, 0.4 and 0.5, reflecting the magnitude of the graph parameter. So in this table 2, we can compare the columns corresponding to sensitivity and specificity. So the first observation is the sensitivity results may not as good as the specificity result. The true result is given in the bottom line. However, if we compare beta equal to 0.4, 0.5, we can see using the larger connection strengths will deliver better estimation results. Yeah, also, if we compare the continuous time modeling with the discrete time modeling, the continuous time method provides more accurate estimation in this simulation study. So this is the first simulation study. In a second simulation study, we want to look at different time lengths t. So we look at a t equal to 1,000 and 2,000. So in this table 3, we can see Using a larger time length, 2000, will produce a better result than using the shorter time length, 1000, for all estimation methods. And in table 4, we want to assess the robustness of our methods using specified time lag, because in the reality, we don't know the true time lag. In the simulation study, true time lag is equal to 1. We can choose a relatively smaller lag, 0.5, and a larger time lag, 1.5. In this table 5, we can see if we use the correctly specified time lag 1, then that gives the most favorable results. If we use the smaller or the larger specified time lags, then this will does not affect too much on the specificity result, but slightly decrease the sensitivity results. So this is as expected. And also, we want to evaluate the robustness of our method to the misspecified conditional intensity model. So in this figure 5, we conduct a separate simulation study to generate the point process data where the conditional intensity function is given in this 34 corresponds to a specific form of the Hawkins process, and evaluate the results. So as we can see from this table 5, most of the results in these situations agree largely with the previous results in table 2, 3, and 4. Yeah, we also provide some additional results, including the performance using the data-driven time lag side. Yeah, I will omit this part. And I also want to present one simulation results incorporating the DAG constraint and ignoring the DAG constraint using the network 1, because the network 1 is actually a DAG, it's a directed acyclic graph. So in this situation, ideally incorporating the DAG structure will improve the performance. So this table results in this table 5 confirm that incorporating the DAG constraint will indeed improve the estimation results. Yeah, finally, we want to study some real-world neuron spectrum data. So we analyze real multiple neuron spectrum data from the medial prefrontal cortex, primarily prelimbic cortex of freely moving rats using tetrodes. Then the recording are conducted during the rat's execution of a behavioral contingency task, as well as during sleep period, before and after the task. Yeah, this data set is downloaded from the public available website. It consists of 90 sessions. Each session represents a different experiment. So in our analysis, we select one particular session, and the spectrum data encompasses a total of more than 1 million spikes from a total of 15 neurons, spanning a duration of about 2 hours. So this is a huge data set. For comparison purposes, we look at 3 approaches. One is our continuous time methods. The other is discrete time methods using the BIC criterion, and the beamwise, which is relatively small, 0.25. And also we compare the linear Hawkins process model as as considered in a 2016 ICML paper. Yeah, we will present two figures. In the figure 3, we consider our continuous time methods. So on the left-hand side, we use BIC, and on the right column, we use GIC to choose the tuning parameter. And within each column, the two graphs, the two plots, yeah, they correspond to the same network, reconstructed network plots using different layout. So the top one use a circular layout, and the bottom one use equilibrium layout. So this figure 3 give us the impression that using the GIC criterion fail to capture all potential interactions in this data. So this figure 3 corresponds to the continuous time method using different type of criterion for selecting tuning parameter. Then in this figure 4, we compare the performance using the discrete time modeling and also the linear Hawkins process. So interestingly, in this case, the discrete time modeling methods using the same weighted L1 penalty and the BIC criterion, they overlap significantly with our continuous time method because in this case, we choose a very, very small bin size, 0.25. So in this situation, if we keep shrinking the king size, eventually the discretized modeling will approximate the continuous time. So this is the discrete time method. But in the real world situation, the continuous time modeling will be more practical because it doesn't depend on the choice of the bin size, and it is particularly useful if the true intensity of neuron specs evolve continuously over time. So continuous time modeling has advantages from this perspective. And also for the linear Hawkins process, we can see that it only detects the excitatory effect. So you only see the red color without the blue color. So this limitation is due to the inherent nature of the Hawkins process because it did not allow the the negative parameterization in the triggering kernel. So overall, the continuous time method can detect both excitatory and inhibitory effects, providing a more comprehensive estimation of the functional connection among this group of neuron ensemble. All right. Finally, I want to provide some conclusion and a discussion. So as a summary, in this work, we aim to uncover the network structure dependency underlying a class of non-stationary multivariate point process models. We develop a continuous time model for the conditional intensity functions. We formulate the associated theoretical framework and derive a probabilistic property for learning the statistical property of reconstructing the network structure. In the future work, we plan to explore the following issue. For example, we want to incorporate additional external covariates, experimental units, extrinsic conditions, or factor into the conditional intensity model. This will make the model more complicated, and also the theoretical study will be more challenging. Second, we want to develop some good in fit procedure to assess the multivariate point process model to fit the real data. And also, we want to apply deep learning and neural network techniques to model and analyze the conditional intensity function, because the conditional intensity function itself is highly nonlinear. Whether the deep learning method can provide new results. This is something we are thinking in the near future. Before I conclude, I acknowledge the supports. I want to thank wonderful collaborations, including former PhD students and postdoctoral fellows. Their efforts and contribution are crucial to this research project. I also appreciate funding from National Science Foundation, Association for Women in Mathematics, and Wisconsin Alumni Research Foundation. Thank you for coming and for your attention.
So, thank you very much. The talk is open for discussion. Are there questions, comments? I see. No. Yes, please go there.
Yeah, good morning. Thank you for this talk. I just had a question on how you choose the delays. You know this phi. You said that you have a data-driven method, finally. Yeah, it doesn't seem to work. Yes, it's about the delays, about how to choose the phi's.
The constant psi, you mean?
No, phi.
The time.
Phi.
Time delay.
The time. How do you choose the time?
The
But then we cannot answer. Yeah, this is. I know.
can just tell her, no?
You go there.
Yeah, I can go there.
So capital phi, the time delay.
Yeah, the constant psi. Yeah, ideally, we don't know the constant psi. Usually, we consider the short-term historical event. So usually, this psi is not big. For real data analysis, of course, we want to learn some domain knowledge. And in practical situation, I guess many times we can use the psi equal to 1. So if psi equal 1 is not satisfactory, of course, we can develop some data-driven method. In our simulation study, we indeed developed data-driven method for the time lag constant psi. So I include the numerical simulation results using the data-driven constant psi. Yeah, that's a good question because it's relevant to practical implementation. Yes.
Sorry, please. Who raised you?
In your continuous model, theorem 2 and 3, you assume that the weights depends on time as 1 over square root of time of t. Is there some experimental confirmation of this kind of decrease?
Yeah, that's a theoretical result. Yeah.
Yes, I understood.
Yeah, that's a theoretical result. You are talking about how to verify that results?
Exactly.
How to verify? You mean verify from proof or verify from numerical results?
How to verify that in your model the weight really depends on as 1 over square root of t.
Yeah.
Decrease like that.
Yeah, this type of result is somewhat different from the conventional high-dimensional parameter estimation. In a high-dimensional inference, usually we consider the number of events, small n, goes to infinity. But in our setup, we are treating the time t. The time length t goes to infinity. Time length t is the in a continuous domain. And the small n, sample size n, is in the discrete domain. They correspond to two separate areas. But definitely some results from the discrete time model in high-dimensional inference can be utilized. So in this situation, eventually the convergence rate is square root 1 over t. Intuitively, this t mimic the small n. Yeah, I would say intuitively, but definitely we need a more rigorous proof. Yeah.
Okay, we can do the same thing. Thank you for a very nice talk.
Yeah, thank you.
I just wondered whether you see any scope for hypergraph modeling here, so to go beyond pairwise interactions.
Yeah, that's a good question because all the results so far are motivated from this neuron spectrum data. In other applications, it is possible that considering other type more complicated interaction would be more relevant. But yeah, so far I haven't thought about it. It could be a very nice future work. Yeah.
Thank you.
Thank you. Thank you for the suggestion.
So I don't see, is that okay? There's one more? So,
yeah, thank you for the really nice talk.
Thank you.
Maybe one follow-up questions on the weights, the omega. So I think in your theorem you had some conditions, I think it was number 28 or 29, on the omegas. And I think that was something like the choice of the omega should be chosen depending on the true beta. So how do you choose and practice the omega such that the theorem holds?
Oh, the omega, you mean the weights?
Yes.
Yeah, weights in the penalty terms. Yeah, we consider different type of assumption for the weights. Some of the assumption are stronger, some of the assumption are weaker. So different type. I didn't talk more about that kind of thing. Perhaps we can check more after this presentation.
Yeah.
Yeah, that's a very detailed part. Yeah.
Yeah. So how you choose them in such a way that 28 and 29 these conditions are satisfied?
Yeah. In the simulation study we mentioned we have BIC criterion, the GIC criterion, and that both work well, especially the BIC criterion provide better results. From the theoretical point of view, probably you mentioned how to develop some data-driven method to satisfy the condition for the weights. Yeah, in the papers, there are some details talking about some empirical choices for the selecting the weights. So that empirical choice indeed incorporates, indeed satisfy most of the assumption for the weights. So that's why they will be, I think they will be doable, it will also be feasible, yeah.
Thank you.
Thank you.
for coming.
Chunming, we greatly appreciated that you came, that your first visit to Germany brought you to Bochum.
Yes, yes.
And so this is a little smell from Bochum for you to take back home.
Yeah, thank you. This is a very unique gift. Yeah, I will. I will keep it. Yeah, thank you so much. Yeah.
Thank you.
Yeah, thank you.